Section 7.1 is on graphing exponential functions. The exponential growth function is f of x equals b to the power of x, where b is greater than 1. The base b is a constant, so it's a number, and in this case the exponent is a variable. Very different from other functions where we've seen where the variable is the base and it's raised to a power that's a number. The domain of this function is all real numbers, and its range is y is greater than 0, where the x-axis is an asymptote. And an asymptote is a line that the curve approaches but never touches. So here's an example of what this basic graph looks like. So as you can see, it from the y-axis, as we move in the positive x direction, it goes up very fast. That's what we mean by exponential growth. And then as we move in the negative x direction, it approaches the x-axis but never touches it. Notice that the y-intercept is the point 0, 1, and 2 points you should learn that are on this curve are the point 1 comma b, where b is the base, and the point negative 1, 1 over b. There's also an exponential decay function, which looks very similar, f of x equals b to the x, but in this case b is a decimal or a fraction that is between 0 and 1. Again, its domain is all real numbers, and its range is y is greater than 0, and again the x-axis is an asymptote. Taking a look at this graph, you'll see that as we move in from the negative x direction, it drops off very fast, and then approaches the x-asymptote as x is getting greater. Approaches the x-axis as x is getting greater. And again, it has the points, the y-intercept of 0, 1, a point 1 comma b right here, and negative 1 comma 1 over b. Now notice that since b is a fraction, that's why we have basically the same letters, but the b changes. So this is going to be, for example, 1 comma 1/4, and this point over here, negative 1 comma 1 over 1/4, which is going to be 4. So let's take a look at a couple examples here. So we need to graph f of x equals 2 to the x power and state the domain and range. So this graph is going to be exponential growth because b, my base, is equal to 2. So let's go ahead and make a table of values and plug in those numbers that we used before. So if I have negative 1, my corresponding y is going to be 1 over b, or 1/2. My y-intercept is 0, 1. And when I plug in 1, I'm going to have the point b. My y is going to be b. Actually, this one is really kind of straightforward. It's basically 2 raised to a power. So if I wanted to put in 2 for x, 2 to the second power is 4. If I wanted to put in 3 for x, 2 to the third power is 8, and so on. But let's go ahead and graph these points. So I have 0, 1, 1, 2, 2, 4, 3, 8, and then over on this side, don't worry about getting too picky. We know what's going to happen here. So it's going to go up very fast on this side, and over here it's going to approach the x-axis. So the domain of this is all real numbers. And the range is going to be the set of all y such that y is greater than 0. Basically what that means is this graph is never going to go below the y-axis. Let's take a look at another example here. Here we need to graph f of x equals 1/2 to the power of x, and again state the domain and range. This is going to be exponential decay because my base, my b, is 1/2. And again, let's make a table of values. And I'm going to use negative 1, 0, 1, and I could actually even use 2, is not too bad. So my y-intercept is going to be 0, 1. My first point is going to be negative 1. Okay, so we had the point negative 1, 1 over b. So let me work through what this is going to turn into. That's going to turn into negative 1 comma 1 over, my b is 1/2. 1 over 1/2 is the same as 2. Basically 1 divided by 1/2, multiply by the reciprocal, you'll get 2. Okay, and then my other point I had here was 1 comma b. Okay, that's very straightforward. That's going to be 1 comma 1/2. And actually you could do additional points if you wanted. So if I put 2 in here, 1/2 squared is basically 1/4. And I guess I could have done a -2 up there. I'll go ahead and put it down here. -2 is going to give me a +4. And again, as we've done with a lot of these functions, you can plug these numbers into your calculator and see the table. So here's my y-intercept, and then I have -1, 2, -2, 4. Oops, that's 5. There you go. 1, 1/2, 2, 1/4. Okay, don't get too worried about that. Just know that the curve is going to go like that and never touch the x-axis. And in this direction, it's going to go up exponentially fast. And again, my domain is going to be all reals, all real numbers. And because this never goes below the y-axis, my range is y is greater than 0. And as we've seen with other functions that we've graphed, of course there are transformations. So like the full-blown idea or parent graph for the exponential function is f of x equals a times b raised to the power of x minus h, and then plus k. And again, you're going to see h and k keep showing up here. So if h is positive, it's going to be a shift to the right. And notice again, this is the minus h going on. So it might look like an x minus 2, but that's really going to be 2 to the right. If h is less than 0, it's going to shift to the left. If k is greater than 0, if k is positive, it's going to shift up. If k is negative, it's going to shift down. A is kind of like the a that we've had out in front of other functions. If it's negative, we're going to get the graph flipped over the x-axis. If the absolute value of a is greater than 1, so in other words, if it's a whole number greater than 1, positive or negative, we're going to have a vertical stretch. And if it's the absolute value of a is a fraction between 0 or 1, we're going to have a vertical compression. So let's take a look at one example of a graph like this. And this looks pretty messy. Graph f of x equals -4 times 3/5 raised to the power of x plus 4 plus 3. Okay, so before we graph this, let's break down what's going on here. So a is less than 0. It's -4. So that means I'm going to be flipped over the x-axis. Okay. The absolute value of a is greater than 1, so that means that this is going to be stretched. And that's all because a is equal to -4. Okay. My base is 3/5, so that means I'm going to have exponential decay. My h equals -4. Remember, it's x minus h, so that means I'm going to be shifted 4 to the left. My k is 3, so that means I'm going to be shifted up 3. Okay, so let's go ahead and probably, this one is really hard to pick numbers and figure out. So to be honest, I put this into my calculator and I came up with some values here. And unfortunately, because of all the stuff that's going on here with the 3/5 and the -4 and the raised to the power of x plus 4, you get some kind of strange numbers. So I'm going to just go ahead and I kind of guessed at it. I got some decimals. I'll put a few of them here in the table. And we're not going to get too picky about, being right on, but it is important to kind of get an idea of what this graph looks like. So bear with me a minute here while I list some of these values. And again, your calculator is a very good friend for graphing some of these. Let's see, 2.5, and I think can I throw one more in there? 2.7. Okay, so let me graph these points. This is going to help us determine what the domain and range are. Let's see, so -6, -8.1. Don't really worry about the 0.1. We'll just go a little bit more like that. -5, 3.7, so not quite -4. -4, 1. -3, not quite 1. -2 is about 1.5. 0, oops, wait a minute. Oh, -2, -1, a little more than 2. 0 is 2.5. And 1 is 2.7. Okay, so you can kind of get an idea. So it's going to be going down that way. So you can kind of start to see what your asymptote is going to be. So this curve is approaching the line y equals 3. So again, my domain is going to be all reals. And my range is going to be y. And let's look at the graph for this. In fact, even look at your values. As you can see, as the y values go up, they seem to be approaching 3 as the graph does here, and it's no coincidence that we actually make k as a 3. So y has to be less than, because the graph is basically all below that, 3. And that's going to be my range. So when you're dealing with a really difficult graph like this that has an a and a fractional base and a h and a k, go ahead and use your calculator, pick some values, and graph it as best you can, mostly trying to determine where is it taking off or going down rather rapidly, and what is the asymptote, the equation of the asymptote that it's approaching. So in this section we took a look at graphs of exponential functions, both exponential growth and exponential decay.